Once the Lewis dot structures are drawn for the molecules, you can then begin to determine the shape or the molecular geometry. Now, the molecular geometry is described by a theory called the valence shell electron pair repulsion theory. And basically this theory says that the lone electrons on the center atom of a molecule will cause repulsion, and that repulsion then will result in some kind of three-dimensional shape. If there are no lone pairs on the center, then the bonds will evenly distribute themselves around that center atom. Some common shapes, common geometries, where there is no lone pairs left on the center, would be the trigonal planar shape at the bottom of the screen. That's boron trifluoride. So boron is bonded to 3 fluorines with no extra electrons on the center, so they evenly distribute themselves. There are 120-degree bond angles between the 3 bonds there. And then the second shape, in which there are no lone pairs on the center, would be the tetrahedral shape there in the lower right-hand corner. That would be something like CH4, where the 4 bonds to the hydrogen from the carbon are equally distributed three-dimensionally around the central atom. And then that shape at the top, linear, anytime you have 2 elements bonded together, of course the shape that they're going to take on would be a linear shape, and that's what you can see in the HCl molecule there. Now, this is actually, again, using the Lewis dot structure to determine the molecular shape. And we're looking at how the electrons are arranged, and are there lone pairs left on the center. And then if there are lone pairs left on the center, what do those lone pairs then do along with the bonds to create the 3D shape? Now we're going to look at 3 different charts which kind of summarize the shapes. This first one I think is organized very well. They give you basically 5 different shapes. We're going to take a look at the 5 geometries, and we want to look at the molecular structure column, which is the second column there from the right. Those are the 5 shapes that I would expect you to know and be able to identify. So the first one there is linear, and if you look at the Lewis dot structure example to the right of the molecular structure column there, that example, you're going to see beryllium in the center bonded to 2 fluorines with no extra electrons on the center. So you will find a 180-degree angle between the 2 bonds because they're going to space themselves so they're as far apart from each other as possible because of the repulsion between the electrons found within the bonds. The second molecular structure down is trigonal planar. The example there that's given is boron trifluoride. So it's always an element in the center bonded to 3 other elements, and then notice that there are no lone pairs on the boron. So those fluorine to boron bonds then space themselves evenly away from each other, and you end up with 120-degree angles between the bonds. The next shape down is tetrahedral. Tetrahedral is a single element in the center and then 4 bonded to the center, and as you can see from the example there, CH4, carbon in the center bonded to 4 hydrogens with no extra electrons on the center atom. So those bonds distribute themselves equally, and you end up with about 109.5 degrees in bond angle. The fourth shape down then is the trigonal pyramid. Now these last 2 shapes both have lone pairs left on the center. The trigonal pyramid shape is 3 elements bonded to the center with 1 lone pair, and that 1 lone pair there causes the 3 bonds to form kind of a tripod shape, and you can see that in the NH3 3D drawing there. And then finally the last shape is the bent or V-shaped molecule. This would be like water, and as you can see, water is the example. Notice that there's 2 pairs of electrons on the center atom, and the center atom is bonded to 2 elements. Now you can also have in a bent or V-shaped molecule, you can have 2 elements bonded to the center with only 1 lone pair. So the key with the bent or V-shaped is there's 2 atoms bonded to the center, and then any extra electrons on the center there will cause it to go into a V or bent shaped molecule. Now if you'll notice, Here are two more very similar charts. There's a couple of extra shapes in this first one, but notice that the second one is very much like the one that we just looked at in detail. So if that first one doesn't work for you, here are two other versions of kind of the same thing. And again, they give you the three-dimensional picture there too, which helps a little bit. So let's take a look at some specific molecules. Let's take a look at water. Now, water happens to be a H2O, so you have an oxygen in the center bonded to two hydrogens, and those two hydrogens then, along with the two lone pairs on the center, create a bent-shaped molecule. And if you look there, we call the molecular geometry bent because you have two atoms bonded to the center and then two lone pairs. Now, that's looking at the bonds relative to each other. If we look at all the electrons relative to each other, the lone pairs as well as the bonding pairs, you actually have four things coming off of the oxygen. So the electron pair geometry is tetrahedral. That is, you're looking at the electron positions relative to each other. The molecular geometry, however, is bent. So you're looking at the two bonds in the molecular geometry. Let's take a look at NH3 in the same way. Notice NH3 in the 3D drawing, you have three elements bonded to the center and then you have a lone pair. So again, just like water, the electron pair geometry there is going to be tetrahedral because you have the four things attached to the center nitrogen, but the molecular geometry is going to be that tripod shape, that trigonal pyramid, where you have three elements bonded to the center, and then you have the lone pair on the top there. So again, electron pair geometry tetrahedral, and molecular geometry there is trigonal pyramid shape.